Well, fitness proportional selection. So remember, like the whole point of the selection strategy is you want it to pick those that are better, but not always, right? You want to make sure you're not destroying diversity by getting too much selection pressure for what you think is good. And tournament selection was a really easy, it was a simple, straightforward, easy to reason about way of doing it. Always picking the best is too much. Too much selection pressure is too much. Or randomly selecting isn't enough. So it gives us that ability that like the tournament size as a dial we can turn to increase or decrease selection pressure. But there's also fitness proportional selection. All right, the simplest of these is to have the probability be the individual's proportion of the total population fitness. Long story short, do I not have a picture? Imagine you had a roulette wheel. And with this particular example here, on the right there's a table showing each chromosome. There's 1, 2, 3, 4, 6 chromosomes, and each of them has some fitness value. These are entirely arbitrary. And with these, you take the sum of the total fitness value, and then you assign that chromosome that piece of the pie. You spin the roulette wheel, and that's the general idea. So those with a bigger fitness are more likely to be selected, but those with the low fitness, it's still possible to select them, which is a good thing. But you're more likely to pick those with a good fitness. So the probability to pick some individual is the fitness of that individual divided by the sum of all chromosomes' fitness. The benefit is that selecting highly fit individuals, the search may produce high quality solutions. However, this may cause us to get stuck at a local maximum. Further, the population begins to converge. The strategy becomes, as the population converges, the fitness, the proportion of each candidate's solutions, the slice of the pie each candidate solution gets assigned becomes more the same. Meaning this selection strategy actually, as you converge, this becomes more like uniform selection. So you lose any like selection pressure there, really. Which maybe that's a good thing, maybe that's a bad thing, but it's important to notice. Modifications to the strategy. Of course, this is just a base strategy, and you can do whatever the hell you want with this strategy. You can do whatever the hell you want with any selection strategy. But they do these things called like windowing. Subtract the minimum fitness within the population from all individuals. That way, you're only looking at, like if the population is converged and they're all kind of around 100, but the worst is like 92 and the best is 101. Well, you subtract 92 from every candidate solution's fitness and then use that difference as the way to select. So that's one way to address it. Sometimes what people will do is they'll add some constant to each of them. A constant is a thing you can tune to just kind of tune how the selection is going to work. There's a lot of things you can do. Rank-based selection. Alternative is to take the same idea but rank candidate solutions and have the probability of being selected related to their rank. So kind of similar idea. Just do whatever the hell you want though, of course. Roulette wheel. So this is the idea of these fitness proportional selections, kind of like in practice. There are some downsides of this though, and what people will say is, okay, do I mention it? Roulette wheels, okay, yeah. Typically the roulette wheel has one arm and is spun lambda times. An alternative is to spin a roulette wheel with lambda arms. You know what, let's not worry too much about this. It's not overly important. And then there's survivor selection. There's two key core ideas that I've just covered. The first one was like your tournament selection, which we talked about how the two extremes of that was random selection and always pick the best. And then we dial it in with tournament selection. And roulette wheel, which is a form of fitness proportional. Both have both are more likely to select candidate solutions that are better, but they do that in different ways, which is interesting. One's not better than the other. Honestly, realistically, in practice, I see tournament selection used more for whatever reason. Roulette wheel also gets kind of weird to work with minimization problems. You can hack it all you want, but it does get a little weird. But those are just two high-level ideas of selection, your tournament and roulette wheel. You can do whatever you want. It doesn't matter. Do whatever the hell you want. Again, just like with the genetic operators, do whatever you want. I was just showing you ideas to just base your ideas on, or to inspire you to do whatever you want, whatever. Then there's survivor selection. Now, survivor selection, if it's a generational algorithm, everyone in the population gets replaced. Everyone only exists for one generation. But with steady state, that's the idea, remember, where you don't have these very discrete populations between generations. You're always picking and putting things back into the same pool. So with the steady state, we need a strategy of determining who is, maybe survivor selection is a bit of a misnomer. Usually, we're not picking who survives, we're picking who doesn't. We're picking who gets replaced, right? You pick two, you apply some genetic operators to them, and you want to put them back in the population. So who do you replace? And for whatever reason, the good people in evolutionary computation decided to call it survivor selection, even though, yeah, it's not that. It's who dies. I guess it sounds nicer than like kill-off selection. I don't know. So with a steady-state algorithm, survivor selection is needed. So any rules could be used, whatever you want. Honestly, randomly replacing isn't bad. That'll work fine. Randomly select some number of, if this is the number I selected, replace that many within the population. Age base, replace the oldest. Oldest being how many rounds of survivor selection has that chromosome existed. The older it is, maybe replace it. Or maybe you make it proportional, still kind of like a roulette wheel, but your likelihood to be replaced is proportional to how long you survived. Whatever the hell you want to do, you do. This one, it ignores fitness, which could be a bad thing, or maybe it's a good thing. Maybe it's a good thing, it's hard to say. But it does risk killing off the best candidate solution. I mean, same with random as well. Fitness-based, replace the worst number, but of course this could cause premature convergence. It happens. Diversity-based, replace those that are the least diverse within the population. Similarity-based, this is kind of like the same idea. It's trying to hit the same core idea, I suppose, where you replace those in the population that are most similar to the new one I want to add to the population. So it's kind of like if it's got a niche, this one usurps its niche. So the first one is diversity about the whole population. The similarity one is more about the one that's going to get added. Which one is this one most similar to? Kill it off. These are all, again, ideas. Do whatever you want, though. And then elitism. This is very standard now. I'd say it's fairly common. Raise your hand if you did elitism in assignment 1. Yeah, it's almost like a requirement these days. The general idea is always ensure, before you do anything, before you do selection, before you do survivor selection, before you do any genetic operators, you always go and find the top X chromosomes, and they automatically survive to the next generation. Unchanged, whatever. You make a copy of them, and you put them in the new population, they're there. That way, you're never losing the best thing. And typically, I see an elitism of 1. Typically, people will do it with really only the best one. You could do it with more than that. It really depends on your population size. If you have a population of 10 and you take the best one versus the population of 100 and you take the best one, obviously that's going to have an impact there. Typically, you only see one, but this is something you can play with. Every problem's different. It's another tunable parameter, really. And then diversity. How much diversity is like now a new section here. Diversity is how much the members of the population differ from one another. And I know I've talked about this a lot, but diversity within the population is so important because it balances exploration and exploitation, and it helps prevent premature convergence. And I don't know, a lot of, we're more than halfway through the semester. And I've been trying to communicate a lot of like really big, arguably like philosophical ideas of understanding how things work. And I don't mean how things work in evolutionary computation. I just mean like how systems work in real life. And I don't know, and I don't think you could, I don't think it's possible for me to talk at you about these ideas and you to understand them unless you spend some time thinking about these ideas on your own. Thinking about them in the context of literally anything you're doing. You could be watching a baseball game and think, how the hell do these ideas relate to baseball? And you'll see them everywhere. You could do this with anything. So when I'm saying something like diversity is important within the population, we have to be very careful. Humans are very, no matter how hard I try or we try to understand evolution, we are still biased by our experience in life and how we like to engineer things. We like to design things for a purpose, right? I want to solve problem X, so I'm going to solve problem X, right? And it's hard for us to kind of think about how nature can solve problem X in a very different way. Because nature doesn't go about trying to solve problem X. Nature just does its shit, and next thing you know, it's figured out it solved problem X by just, it fell ass backwards into it, right? Right? It's kind of hard to, again, I don't know if these ideas, if you truly understand what I'm talking about, because if you haven't spent the time to think about them, it's probably difficult. When we are designing a solution to a problem, if I'm an engineer, and I'm designing a solution to a problem, I'm not thinking about evolutionary computation right now. My goal is solve the problem. And in the context of evolutionary computation, solve the problem is fitness. Okay? But we are so biased as humans because when I want to solve a problem, I want to solve a problem. And I know what's good. Fitness is the measurement that's good. That's what I care about. Fitness is the important thing in an evolutionary algorithm. But it's not. Obviously, it's important. But that metric is one of two big metrics. It's related to one of two big core things: selection pressure and diversity, the variation operators. They need to be there together. So we tend to get so focused on fitness that we lose the idea, we take for granted the diversity aspect of our evolutionary algorithms. And we often think about, when I design my algorithm, obviously fitness is what I care about, and I need to kind of manage diversity while I focus on the fitness, right, to make sure that my diversity levels are good for fitness. But something happened about a decade ago, maybe not even that long ago, maybe like 7 years ago, where some researchers flipped it. And they said, no, focus on diversity and keep the fitness at bay to preserve diversity. And they got some wild, crazy, important results. And these are some of these researchers are the most important researchers in the area right now. This is all to say that don't get so focused on fitness that we lose sight of how important diversity is as a metric within our evolutionary algorithms. there are some things we can do with our evolutionary algorithms that very explicitly encourage diversity. Things like, I mean, what you were talking about with TSP, how you created like your diversity metric and you tried to incorporate that into your algorithm, right? That was a very explicit thing. But there are other things where some people will add things to the algorithm for where its goal is to improve diversity, but it doesn't do it in a very direct way. It's a consequence of how the algorithm works. It encourages diversity. And these tend to be really popular because they tend to be kind of easy to implement, have some other added benefits, and of course, increase diversity, which overall increases the actual effectiveness of your algorithms. So, like everything, there's no rules about what should be done. But here's one, the island model. Instead of having one population, what you do is you have maybe 3, 4, 5, 6, 7 populations. And they evolve independently. During evolution, everyone from population 1 can only ever be selected and crossed over with things in population 1. Things in population 2, similarly, things in population 3, similarly, etc., etc. They evolve independently, but every once in a while, let's hit pause. Well, why is this good? Well, look, if we've got a complex search space, we've got a lot of local maximum, a little local minimum, a lot of different areas of the search space. When I hit run, if I've got a sufficiently complex problem, you know, the type of problem we're actually going to use evolutionary algorithms for, every one of these populations will start to converge probably on different parts of the search space. So diversity among each population starts to become low. But then every once in a while, you allow migrations. How you allow migrations is entirely up to you. Maybe you pick 2 or 3 from here, bring them over there, 2 or 3 from here, bring them over there, there. Maybe you just have like a free-for-all, you put them all together, you shuffle them, you split them back up again, whatever. It doesn't really matter too much. That's just another tunable parameter and everywhere in between, of course. But this tends to be really great because it encourages diversity and in a way where it's kind of, I don't even need to do too much direct intervention to encourage diversity. I don't have to do any direct intervention. I implement the island model and I hit go and it's good. I don't have to go measure diversity. It just encourages diversity to begin with, and you end up getting really good results. And then I'd also point out that evolutionary computations have been called what we call like embarrassingly parallel. Has anyone ever heard that phrase before? The algorithm is so trivially easy to parallelize that you should do it. Ignoring the island model for a second, if I've got a really big population, the slowest part of any evolutionary algorithm is the fitness calculation. Maybe it's a linear time algorithm, but if I have to do that on each chromosome in the population for each generation of the algorithm, and I mean, we're talking about like 1 million generations and population size of 1,000, we're in the billions of fitness calculations, and that's that's a lot. So, parallelize it. Fitness evaluation, the fitness of one candidate solution is nearly always independent of the fitness of another candidate solution. It doesn't matter. So you can evaluate the fitness values in parallel. Now, unfortunately, in practice, a lot of times when doing that, the added like computational overhead of your system of creating threads and running them on different processors, et cetera, ends up being more of a pain than it's worth. It ends up taking longer to parallelize it, just not because the algorithm's slower, but just by how this computer has to work to do it. couple years back, I tried to do a similar idea, but with like a GPU, where I offload all the work to the GPU to evaluate each candidate solution with the particular problem I was working on. It was just doing some floating point calculations, so it was perfect for a GPU. But I'd have to like send all that work to the GPU for each generation, and the overhead and the bus speed and everything of communicating between the bits of the computer was so slow that it really wasn't worth it. So although it's parallel, it's embarrassingly parallel in theory, in practice it ends up being kind of, well, you know, whatever. However, if you do something like ring species, well, now it's a little different. If I have like 4 actual cores or 8 actual cores on my computer, well, I can have them each run on their own core. Great. And although there's no parallelization between the fitness calculations within the candidates, within the populations, each population is being evaluated in parallel. Okay? So there's some added benefit there. But given, let me put it this way. If you are running a giant-ass search and you need to use some like heavy-duty computers, like Compute Canada resources, like Canada's research supercomputers, and you have a job like this set up where I'm going to use a core for each population, each island population, they're going to get mad at you because of the stochastic nature of your search. It might take 1 second to evaluate the fitness of population 1, and it might take 3 seconds to evaluate the fitness of population 2, and it might take 4 seconds to evaluate the fitness of population 3. Meaning population 1's core is going to be waiting a total of 3 seconds. Population 2's core is going to be waiting 1 second. It's just going to be waiting on that other core. And so you are actually now wasting time by kind of like waiting on them. So usually, in spite of how easy this looks like to parallelize, in practice, if you have 8 islands and you have 8 cores on your computers, usually it's better, to set your algorithms to run with however many islands you want, 8, and instead of having each island run on each of those 8 cores, usually it's better to have them all run on the same core, but just run the algorithm 8 times at the same time. So your computer, the operating system, is managing all of that. So each process will run on its own core. Just as a heads up, just as a warning. If you're like, I'm going to parallelize this, by all means, but don't be surprised if you make it worse and slower. I know, it's sad. And then here's another idea. This one's really good. This one only has 1 population, and we pretend the population is like a ring. It's called like automatic speciation or something. I can't remember. But when you do selection, you select one candidate solution, but that candidate solution is only allowed to mate, to like be crossed over with a candidate solution that is within some distance from it. So the idea is, and this was inspired from, and the guy that came up with this idea I actually worked with a lot, and he recently passed away. The idea was, and this happens in real life, where you'll have like a giant-ass mountain. Here's the story. I don't know if the story is what happened in real life, but this phenomenon will happen. Is like there was this like mountain somewhere in like Central America, I don't know. And there were these like lizards or something that lived around the base of this giant-ass mountain. I don't mean it was big, tall, I'm sure it was, but I mean it was like maybe a big mountain range or something, right? And they were all like the same species. Now you got to remember, humans love to categorize things, but unfortunately nature is kind of categorized phobic. It's kind of doesn't, like we are trying so hard to categorize things. So we can be like, they're the same species. Then it's like, well, where do you draw the line between what is and is not the same species? How can you tell and all that, right? We love to create these discrete categories for things that aren't discrete. So they're the same species, but they found that, like, even though they are, those little lizards from this part of the mountain, the further away you went, the less, like, they couldn't actually produce offspring. So just by nature of this, like, geographic restriction, it actually created this bit of like of an issue isn't the right word, phenomenon, right? So that was the idea here. Well, we can actually create this, like, diversity. We can encourage diversity implicitly within the population by adding this restriction of, like, well, who could you actually produce offspring with? And then it encourages this, like, spectrum of diversity, which is really good. And then periodically, maybe you allow, like, a shuffle within the population. Suddenly, now you will allow things that are diverse to actually mate with one, and now you get wild, different result. You can do whatever you want. Again, these are just ideas, base ideas. And, like, who here agrees that this idea, although maybe you wouldn't have come up with it, would you agree that this is a relatively simple idea? He produced, like, there are so many published articles around this basic simple idea. You could do the same thing. You could, when I'm talking about doing your final project, I'm not sure you understand that you could come up with your crazy harebrained idea, and suddenly it's, like, actually a big fucking deal. So, you know, come up with your crazy idea and maybe it works. It doesn't need to be overly sophisticated. Computer scientists, you're all notorious for trying to make up with your complex, crazy shit because you love it. Keep it simple. And maybe your crazy, simple idea will work to the point of, like, hey, wow, good results. Cool. Finally, how does one actually measure diversity? And that's kind of the problem you ran into when you're working on TSP, is you came up with your metric. Do you think it worked particularly well?
As measuring diversity,
yeah. Right, so there you go. But did you measure diversity on the, I mean, it's TSP, right? So the genotype and phenotypes are actually, it's a fairly direct representation. But there's no hard rule about how you measure diversity. Do you do it in the genotype space? Do you measure diversity on the encoding? Or do you measure the diversity on the phenotypes? It might be very similar to what it would be in the genotype space or not. It's hard to say. How do you want to measure it? Well, it depends on the encoding. Should you do, like, a Hamming distance, 11 times, like, what distance metric should you use? I don't know. It's up to you. There's no right answer here. Anyways, any questions about any of that? All right, genetic programming. So, this is a bit of a shift in topics now. Genetic programming is, at the end of the day, this whole course is on evolutionary computation, which is a huge umbrella term, but the big focus has been more or less on genetic algorithms, because genetic algorithms are the most popular, and it is probably the most true to form of the idea of what an evolutionary algorithm, what evolutionary computation is. And all other forms, they're all related to one another, and you can play the game of reduction from one to another. But a GA really is the most, I don't want to call it the most basic, let's call it foundational. So the sheer fact we haven't had a topic on differential evolution shouldn't throw you off, because differential evolution is, it's a GA, but you do X, Y, and Z instead. Evolutionary strategies is the same as a GA, but you do A, B, C instead, right? Like, it's all, like, they're all so similar. Now, genetic programming, now this might piss some people off, it's just a GA. It really is just a GA. And that, but what you do instead is so, it's just, what's special about genetic programming is the encoding. That's it. It's a GA, with a narrow category of encoding. So a genetic programming is a genetic algorithm. A genetic algorithm where you use this like tree-based encoding we're going to see, well, it doesn't have to be a tree-based encoding, but it's the spirit of what we're getting at. It's just a GA, all right? So genetic programming is a GA for evolving programs and functions, though. So the genotype is typically a tree structure representing the program function phenotype. And the genetic operators, just like everything, are going to depend on the encoding. What genetic operators are you going to use? Well, it depends on what your encoding is. Is it a real number encoding? Is it a floating point number? Is it a permutation? Is it integer? Is it bits? It depends. What genetic operators you're going to use depends on the encoding. There's no special difference here. It's not special. They're not special genetic programming. No, it's special genetic operators for the representation. And ultimately, it's a genetic algorithm, but the search space is a narrow category of like the programs and functions. So consider this right here, the breast cancer identification. This is a classic data set available from like the UC Irving machine learning data repository. It's been around for ages. I wouldn't be surprised if this is built into like scikit-learn as just like a package you can import, or data you can import from scikit-learn. But you can go and you can download it from, do I have, yeah. Is anyone who here is not familiar with UC Irving's data repository? All right, no one is. You should be. Anyways, it's a giant repository hosted by UC Irving of this data that you can use for like playing around with your machine learning algorithms to kind of like benchmark and test them out. They're all fairly standard and whatnot. Now, mind you, a lot of these have been around forever. But anyways, this data here, here's some data I've taken. So if you go and you look at the data, this is that data, but I've reduced the number of columns. I've reduced the number of features just for representation purposes, all right? So here is what the data looks like. Consider the problem of detecting if an individual has breast cancer. And here's some metrics that we have. Patient ID, probably not overly important. Thickness, size, shape, bare nuclei, mitosis. I don't know what these mean specifically in the context of breast cancer, but these are the metrics we have, the measurements we have. And then based on that, we want to know, is it malignant or benign? That's the goal. So we want to identify malignant or benign based on this data here, right? It is formulated as a typical classification problem. Ultimately, what I want is I want a function that takes thickness, size, shape, bare nuclei, and mitosis, and returns benign or malignant, right? It's a function that takes these as arguments and returns the class. It's a basic classifier. All right? Any questions, thoughts, concerns, comments about that? All right. So the goal is to build a classifier to determine if a patient has breast cancer based on observation. So what should the classifier be? If size is greater than 4 and shape is 3 or shape is 5, then malignant, else benign. If thickness is greater than 4 and thickness is less than 9, then malignant, else benign. I mean, I'm pulling these out of my ass. It would take so much careful study and a deep understanding of the problem for me to sit down and build this. And experts in the area aren't building these classifiers because they can't do it either. It would take forever. No one's going to do it. But this is where AI and machine learning show up, right? I don't want to build it, but maybe I could show my program a shit ton of observations of the data and it can figure it out on its own. That would be nice, right? So we want AI machine learning to generalize trends that exist within the data to produce our classification for us. This is your typical classification problem. And I'm formulating it as a machine learning problem because I don't want to build the classifier. I want to use some fancy mathematics to build a classifier for me. That's what I want to do. So far, so raise your hand if you've taken machine learning. Okay, good. So this should be easy for you. For the 3 of you that didn't raise your hand, so far so good though? Yeah? All right. So in general, evolutionary computation is an optimization strategy. But if you can formulate your algorithm such that you're optimizing something, you can use it. And if our goal is to optimize like classification results, great, we can do that. So that's where we can use evolutionary computation. And the way to do that is with our encoding. We need to make our evolutionary algorithm evolve classifiers. And then the evolutionary algorithm will optimize those classifiers that it's evolving classification accuracy, correctness rate. Okay? Yeah? So far, so good? Yeah, so this is where genetic programming comes in. So we use S expressions, symbolic expressions. This is your typical encoding for genetic programming. They're used to represent nested instructions in data, and these S expressions are commonly visualized as trees. So here I've got 3 separate S expressions, and these are from like a broad, they're all doing something different. They're not really related to one another. This S expression evaluates to 1.2 minus x times y, to that. All right? Does this make sense? This is an operator that takes, and that operator takes or needs 2 operands, right? Here's one. Y is like a variable. So if I had like f of x and y equals this, right? Does that make sense? I'm seeing literally stone faces from all of you. I don't know if you're happy or sad or whatever. Okay, I saw 1 thumbs up. And someone go like, which was you, because your mouth was covered. Right? So there's a value, and it needs another value. But over here, this isn't an operand, it's an operator. And this is one that takes 2. Well, it needs 2. But if this operator can get 2 operands, it turns into an operand, right? Yeah? Yeah, all right, cool. These are internal nodes, these are terminals. And the terminals are either going to be some constant value, right? Or some like argument parameter, variable, right? Here, we've got length is less than 5.2 or not red. I don't know what this is for, but this evaluates to the Boolean expression. Length less than 5.2, that's going to return a Boolean. And that's going to get ORed with not red. So presumably length and red are going to be some features of the observation. Is it red? Yes or no? What's its length? Right? Now what's neat about this one, over here, this one only works with numbers. Right? There's only numbers in here. You could say, well, no, that's an operator. Yeah, but this evaluates to a number. What's interesting about this one is this actually has multiple different types in there. We're dealing with numbers and Booleans. And then finally, here's another one. It's got like an if. And what's neat about if is if requires like 3 values. It requires a Boolean and then the like true, false return, right? So if open and right closed, forward, else turn right. So that's what that evaluates to down there. So this is maybe like an instruction for a robot moving through a maze. This could be a classification of some flower, right? I don't know. And then one on the left, that's just some mathematical expression. All right? Okay, consider the above program function above. Someone going to make a pull request to fix that? Because that's egregious. For the best consider the above program function above for the best breast cancer identification problem. If size is greater than 4 and shape equals 3 or shape equals 5, then malignant, else benign. The true means malignant, false benign for this, because this is a Boolean expression. We don't even actually need the if. If this evaluates to true, we'll say malignant, false benign. I can represent this as the tree, size greater than 4 and shape equals 3 or shape equals 5. All of this is going to evaluate to a Boolean. If this expression evaluates to true, it says it's malignant. If it's false, it's benign. This is just an example. Obviously, this is probably not a very good classifier. But this is just showing you how we can encode that as a tree. Any questions? Or are we all happy? All happy. When I decide on my encoding, if I'm go back to a GA. If I'm evolving TSP, solutions for TSP, I have a permutation representation. I need to tell my algorithm what are the allowable numbers for your encoding, right? And you're like, well, it's going to be a permutation of the cities 0 through n minus 1, right? That's what you're going to do. If it's a binary encoding, you're basically saying, okay, you're going to have numbers that are either 0 or 1 in here. When you use integers, maybe you're allowed to have any integer in your encoding, or maybe the integers mean something. And maybe you only really need integers between 0 and 4 to be in your coding. But you specify, you restrict what's allowed to be in your representation. The same idea is here with genetic programming. We're going to use S expressions, but what things are we going to allow within our chromosome? The set of available operators and operands, operator being something that, an operator is like, remember, raise your hand if you remember learning operator and operand when you were about this big. Maybe about that big? Okay, fine. Operator is like addition, subtraction. Operand is a value that is applied to an operator, right? You can think of these operators as functions, right? They really are just functions that return a value, right? So operators and operands are used to create the tree. But what are we going to allow in our trees through evolution? I got to start with an initial population, meaning I got to start with a random population of TSP instances. I need to start with a random population of trees for my genetic programming. What things am I going to allow in there? Well, maybe for the breast cancer problem, I might use something like this. The operators, I'll have a bunch of binary operators, plus, minus, multiplication, divide, less than, greater than, equals, and, or. These are all binary operators, but be aware of the different types here. Plus, that's an operator that works on numbers, and it gives you back a number. Works on numbers, 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 but it gives you back a Boolean. This is a comparison operator, not an arithmetic it's not arithmetic, right? So this is a Boolean. Another Boolean one, it takes numbers and gives you back a Boolean. I mean, equals doesn't necessarily take numbers, but it takes something. Is everything going okay there? Doesn't look.
The phone kind of dropped it a while ago.
Yeah, all right, good luck with that. Hey, classic. Checks if things are equal. It returns a Boolean. Now the AND and OR, they're binary operators, but they're even a little bit more different. They take Booleans and give you back a Boolean. So be aware, although they are binary operators, the operands the type of the operands they expect and the type of the value they return might differ. Does that make sense? Right? Good, because this is like grade 4, right? Grade 2? I don't know, whenever you learn that. And then unary operators. Maybe I want sine, cos, e, not, whatever. Why might I want them? I don't know, I just put them in there. Maybe they're a bad idea to include. Why didn't I include tan? I just didn't. Maybe I should have, I don't know. I'm just showing you an example. And then for the operands, maybe I'll have some constants, like for, true, false, and the variables, the size and the shape, right? Like thickness, size, shape, bare nuclei, mitosis. Those would be like the variables. And then finally, here's when working with mathematical expressions only. Now, take your mind off the breast cancer classification. When dealing with only mathematical operations, the language is just going to be a collection of mathematical operators and operands, like numerical operators and operands discussed above, which keeps things nice and simple, which is nice. Anyways, any last questions? All right, I'll catch you later.